Dr. Jonah Gelbach from Berkeley. He is not only an economist, and
Not just.
not an economist, but he's also a law professor and a very distinguished law professor. And today he will present to us some of his work that relates more to economics. And he wants to expose us health services researchers, or in our field of dementia and disparities, he'd like to introduce some of his methods. So without further ado,
Thank you, Warner. I did say that Igor wanted to expose you to my methods when I consented. But it's been very interesting for me so far. I don't know really very much at all about Alzheimer's research or related dementias, but I do know a fair amount about statistics. Before I went to law school, I was an economics professor, and statistical methodology is part of my focus. So it's been very edifying so far for me. The discussion that I'm going to start with in just a moment is one, and I think I go to 234, is that right? For this session. Okay, the discussion I'm going to start with in a moment is deliberately very simple. I'm going to have some things to say about less simple versions and why they're relevant, and some of that will, I think, connect with some of what Igor was just talking about as well. But I hope I don't lose you on the simplicity, because again, it's deliberate. It is unavoidably, from my perspective, outside of the topic area in a particular kind of way, because as I said earlier, I don't research in this field. But you can, I hope, walk with me, and I'll sort of make the obvious comments about how to translate what I'm talking about into effectively change the dependent variable in your mind. So hopefully that won't be too hard. Okay, so this paper, I should say, what I'm going to talk about comes from a paper of mine, which is how Igor got in touch with me, called When Do Covariates Matter and Which Ones and How Much, which is about decompositions of observed effects into different kind of potential explanations for the observed effects, and doing it in a conditional way rather than a sequential one. Something Igor alluded to a bit in his talk as well. It's not a new paper. It's a 2016 paper. I am working on an extension of it, and I basically know the results already. I just haven't finished writing them up for nonlinear cases. This discussion will be focused on linear regression style cases, but I'll say more about that. If anybody wants the slides, I'm happy to give them to you as links to the papers I mentioned in the paper. Okay, so a standard thing that social scientists hopefully do a little bit less often now, but used to do very often, is to start with some base. Well, I'll talk about what I hope they do less often in a moment. This is fine. Start with some base model. This is a model like where there's, if you're interested in disparities, and you're specifically, for example, interested in racial disparities, you have a dummy variable for the particular racial group of interest, and you just estimate some baseline model that has a dependent variable on the left-hand side and just a constant dummy variable for the racial characteristic of interest, and that might be the base model I'm talking about. It might also be a model that includes, say, adjustment for age or ethnicity, or other kinds of things that are part of one's notion of the base model. In economics, one would often see people estimating a model like this, where, as I'll talk about in a moment, the dependent variable y is something like log wages. If you want to think about that as like log prevalence of Alzheimer's in a particular area, you're just basically in the same place statistically from there forward. But it happens that this example is one that involves wages. And X1, in my case, well, I'll talk about what X1 is in a moment, but it's the sort of base set of covariates. Now, a common thing that one sees, and this is something that Igor discussed, and I think we had a presentation or two in the morning that also mentioned this sort of thing, is to add to that base model various subsets of some covariates. And I'm going to use the term X2 for the full set of covariates that are out there. Not important what exactly they are for the moment. But there's some some collection of them, and then there's a partition of them into capital M groups. Okay, so you can think about it as, demographic SES characteristics we were just talking about, and, local area measures, economic conditions of the area, what have you. Those are the kinds of things that might be X2s. And as we add them sequentially, as a common thing to do, once we're done adding them all, we get to some full specification that has all of them in the model all at once. Okay, and that's usually the specification that the researcher sort of considers the best one, leaving aside issues related to averaging, which I'm not going to talk about in this paper, although I'd be happy to talk about afterwards. But there's some sort of belief that the real model has to include all of these things, so it's that full model that's ultimately of interest. So why would people do something like that? There are two reasons that I would commonly hear when I ask people about this. One was to assess whether the estimate of the coefficient on the thing we care about, X1, for example, the race dummy coefficient, is that robust? Like, this is a very big concern in economics for various reasons, having to do with focuses on causal inference and identification. Well, if the X1 coefficient bounces around a lot when we add new variables, the thought goes, well, then it must be that there's all these other mediators, moderators, confounders, and they are driving part of what we're observing. And so maybe we should be more skeptical of the results in general. I think that's a common intuition. I'm not going to go into greater detail. That's just what people would often say to me when I ask them, why do you do this? Why do you think it's reasonable? And then the second thing, more apropos to today's meeting, is that as we add these explanatory components, as we go from the base model to the one with the first set and then the second set and so on of covariates, somehow we're getting some marginal impact of or explanatory value of these additional covariate sets that are being added, and we could maybe speak loosely, goes the argument, that when we add, economic conditions or SES measures, that we're picking up the share of the full difference that's attributable to those kinds of to variation in those kinds of variables. So that's a common thing I would hear, and it's not that hard to find it in a while. So I want to give you now an example. This is a very deliberately simple example from my paper. It's based on data from the National Longitudinal Survey of Youth. So the opposite end of the age spectrum from the HRS and many of the other data sets that you all have been talking about. But this is a common data set for folks who are interested in studying the determinants of wages, particularly for younger and now, given that this is a 1979 cohort, now prime age or even older workers. So this was just based on another paper by Neil and Johnson. It's not important what that paper was about. And actually, this also comes from a comment somebody else wrote about that paper. Again, not important for our purposes. So here's the base specification. We have log wages on the left-hand side. The main focus is the difference in log wages across race. So there's just an indicator variable for whether a particular person in the data is Black. And we see a 22.1 log point difference. So way lower wages for the folks in the relevant age group in this data across race. Blacks have much lower wages. The base specification here, so what's my X1 in this example? Well, there's the thing I really care about in this world, which is this dummy for race, but then there's also another couple of variables that are part of the base specification. They're just there because like everybody thinks age matters for earnings. And the same reasons that you might think that race matters, you would think as well could explain why ethnicity would matter. So this is that nobody would run the model without these three variables, without these other variables is sort of the idea. Now, in this hyper simplified example, this is not really what economists would normally do in estimating wage equation, but I wanted to demonstrate a point using it. The X2 that we're thinking about is just two more variables. Okay, one is years of education. I believe it's just years of completed education. And the other is the Armed Forces Qualification Test Score, which the LSY has. It's like some people think of it as IQ. I don't mean to suggest there's anything special about IQ and such, if you want to think about it that way. It's just a test score that measures for younger people their aptitude in various dimensions. And so those are our two X2s. And if we include all of them at once, we have this full model. And so you see, yes, 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 all three of them included. And we see that, wow, the difference in the log wage gap, the black-white log wage gap in this fully conditional specification, the full model versus the base one, is pretty big. Like a 10 log point wage difference is big. Just take my word for it if it's not obvious to you. And so we've explained, almost half of the black-white wage gap in this sample, in this population, as an estimate using these two variables. So then the question becomes, well, what if we want to figure out how much of that is education and how much of it is AFQT, right? How much is one versus the other? So one thing that somebody might do is start by adding just education, right? So they still have the race boundaries and the other variables, right? All the X1s are always there. And they add just education, but not AFQT. And then do some stuff, which we're going to talk about in a minute. But then the other thing they might do is the opposite order, add AFQT first by itself, and then add education. And do the same kinds of things, but with a different order. So does it matter? I got very lucky with this example. It does matter quite a lot. So here's the add education first. So the sort of specification order one. And look at that. We've narrowed the black-white wage gap by 2.5 log points. Okay, so we're decomposers who are doing the sequential thing. We say 2.5 point explanatory value for education. Of course, that leaves the difference between 2.5 and 10.4, which is to say 7.9. Well, it looks like test scores are kind of doing most of the work, and education is not that important. What if we do it in the opposite order? So if we do it in the opposite order, we add test scores first, we find the gap is 7.2 log points. So wow, we've explained basically 15 log points. Right? It's almost 2/3 of the gap. We actually explained more than the full gap, right? By just adding test scores. This is in, I've got two mistakes here just to really emphasize the problem. Instead of this minus 14.9 being on this row, it should be on this row. And then the number that's going to come up, I think, is also going to be an error. But before I do that, let me show you the right number, which is actually, when we then add education, it looks like with this sequential decomposition approach, it looks like education is actually causing more of a wage gap. Wow, education makes it worse. That's what you would draw from this, right? Bad to get more education from a wage differential point of view. And now, so see, this should be 4.5, except it should be up here, and this should be minus 14.9, but down here. All of this. Okay, so you see the problem, right? The order in which we add these leads to very, very, it doesn't even matter where they are, right? The point is, none of them can be right, okay? The reason is straightforward. I think everybody in this room probably understands. Education and test scores are correlated with each other. They're correlated with race, and they're correlated with weight. So this idea of doing one at a time is really problematic. And again, if you want to turn this dependent variable from wages to some measure of Alzheimer's or dementia-related considerations, then almost everything else I'm saying would just follow as not the numbers, obviously, but the problem. Okay, so what to do about it? Here's the solution that I offer in this paper. And I just, before I get there, let me just say this is the full specification, right? Full model at the estimated values. So there are hats there to show that things are being estimated. It's just a property of, I think of the data as being in vector and matrix form, right? So this is all the Ys, all the X1s, and all the X2s. It's a property of linear regression that the fitted values of Y equal the actual values of Y once we add in the estimated residuals, right? So this is just an identity. The nature is part of the fact of what it is. And beta 2 happen, I won't distinguish base or full. This is the full model always when I use beta 2 hat. So the first thing I'm just going to do is move this x1 beta hat full term over to the left-hand side. I'm going to subtract it. And then having done that, so you'd say y minus x1 beta 1 hat full. I'm then going to pre-multiply by the thing I would use to create the base model least squares estimate, right? Which is x1 prime x1 inverse x1 prime. If you look at this for a second, well, here, just pointing out that what's left is this stuff over here. The first observation, this is a fitted residual from the big model, but x1 is in the big model, and so it better be orthogonal to the fitted residuals from the big model. So that term is going to go away. It's identically zero. Okay, so now I want to go look over here. If we take this first part and throw a y at it, that's just the base value of beta 1 hat. That's just the beta 1 hat base, right? By construction. And then if we look at x1 prime x1, right, that's going to annihilate x1 prime x1 inverse. And so it'll go away, and what we'll be left with is beta 1 hat full. And so when we work through this, what we find is that the difference between my base column estimate for the black-white wage gap and my full column estimate, that's what's left on the left-hand side, right? It's just that observed difference. And lo and behold, it just equals, and this is the sample emitted variables bias formula for those of you who are remember that or familiar with it. And I'm going to do some stuff with this to make the decomposition work. Turns out that the conditional decomposition works by leveraging the emitted variables bias formula. Not something I realized until I thought about this for a long time. So just define this as that difference, right? It was 10.4 log points in the table I showed you. That's delta hat. It equals, there's beta 2 hat, right? And so I've just taken this gamma hat and defined it as x1 prime x1 inverse x1 prime x2. It's essentially the projection of all the x2 columns into the x1 space. So it's like running a whole bunch of separate auxiliary regressions of the x2s on the x1s. I want to point out one other thing, which is for this delta hat, for this difference to be non-zero, there's a necessary condition that both gamma hat, that matrix be non-zero, right? If the x1s and x2s are totally uncorrelated, then this thing's going to be zero. So like in a random assignment trial, right, you'd expect that these would, the added x2s would be, orthogonal to treatment assignment if that was our x1 of interest. And so this gamma thing would go to zero. So we'd have no bias. We're all familiar with that intuition. Also, if x2 doesn't matter for determining wages or whatever our dependent variable is, then beta 2 hat is generally going to be zero or close to it, right? And that'd be enough to get us zero. Both of those are enough to get us to zero. So if we want a non-zero, if we're going to have bias, we need both of them to be non-zero. But that's not sufficient, right? Because they could be orthogonal. It could be that the association of x2 with all the x1s is actually uncorrelated essentially with the impact of the x2s on the dependent variable. And weirdly enough, I found an example of this totally by accident in the paper that I mentioned. So I've seen other examples in subsequent papers people have written. So it's not like a total knife edge weird result. It's a real possibility. And so I just want to mention that just because you find that the full and base models have similar beta 1s does not necessarily mean that x2 is irrelevant. It could just be that this kind of orthogonality thing I was just talking about happens to hold. All right, so that's the end of that part, the sort of the worst of it, I think, slide-wise. But we're going to do a little bit more with equations. So I want to just remind you, right, this is just taking from the previous slide. This is our bias, right, or our difference, our delta hat. And it's gamma hat times beta 2 hat. So in my example, we start over here. The black-white education gap is what gamma hat education black is. And it's about a third of a year in my data. Also, education, comes from the full model. I didn't show you these estimates, but you can find them in the paper somewhere. The impact of another year of education in the full model is about 4 log months. Okay, so what that's telling you is that the part of that 10.4 log wage gap, log wage gap that's attributable to education conditional on the inclusion of AFQT, of test scores, when everything's in the model at once, is about 1.5 log points. Okay, it's just the product of these two things. That's just working through this algebra. You do the same thing. The test score gap is, I think this is standardized, so I think this is in standard deviation units, I believe. So it's not quite a full standard deviation test score gap, not a small gap for this population. But it turns out test scores are like really associated with wages in this data. There's 10 log points to go up a standard deviation, and it's nearly a standard deviation different, right? So we got about a 9 log point. So if you add these numbers together, look, they're 10.4. And that's an identity, right? This is always going to equal the observed gap. That's the stuff that I basically just wave my hand at, but it's easy to prove it precisely. So that's the conditional decomposition. They might be thinking, well, geez, Gelbach, in the real world, we're going to have like tons of variables, lots of X2s we care about. They're also going to be dealing with nonlinear things. We're going to care about that too, but hold that thought for a minute. We're going to have all these variables that you really want me to sit there and like type out all this stuff. And, sure, you can write code for it and stuff, but surely there's a better way. And yes, there is. When we have a lot of X2s, so K2 is the number of these X2s, it could be a pain to do the decomp this way. So I'm just going to like really rapidly show you the way to think about this. Here's our bigger formula. Again, this whole thing is gamma hat. So stop thinking it is gamma hat times beta 2 hat. We're going to collect the X2 beta 2 hat part now. And we're going to observe that that's just the sum over all the X2 covariates of the covariate specific version of that. And then I'm going to relabel this product X2K beta 2 hat. Okay, and I'm going to call that H. And H is not an accident, it's stands for heterogeneity. So this is the heterogeneity associated with the kth X2, right? Okay, what good does that do me? Well, I just want to observe that once we have the sum of H hats here, we put that up here, we realize that we can think of delta hat as just a sum of the coefficients from a bunch of auxiliary regressions of each of these H hats, right, on each of these heterogeneity terms on the X1s. So if we were to stick, the first one up there for a second, we'd say, oh, well, that's just the like simple base model, except with H hat 1 instead of Y on the left-hand side. And that would be true for each of the other Ks. And all of a sudden we realize, well, this is just like, we create this model version of heterogeneity associated with conditional heterogeneity associated with the K X2, and then we run a bunch of regressions and add up the results. And that's always going to exactly equal the observed base full difference that I showed you on that first table. But it's better than that because we can take sets of the X2s that are kind of conceptually associated with each other. So whatever you mean, whatever Igor means when he says SES, when he says socioeconomic, which are conversations with education, but it could be more than education. It could be like your parental, your parents' jobs, or all sorts of other variables that we think of as SES. Collect those all into one set, create this H hat for all of them at once, and just run one auxiliary regression. That gets us the part of this explained wage gap that's attributable to those SES variables. We do that for area. We could do it for age dummies if they weren't already in the base model, and so on. Okay, and so that's the speedy way to do all of this, and that's really all I'm going to say about algebra. I'm going to now make some more general points. The method here allows you to run G auxiliary regressions, where G is the number of groups you care about. So if you got 4 types of variables, just collect them the right way, and you only have to run 4 of these things. Okay, so and all of this is like numerical identical stuff. This is a true decomposition in that product. All right, so additional decomposition. You're probably saying, Gelbach, that's fine, but what about variance? I'm like a statistician. I want to do inference too. So This was not a lot of fun to write the code for. More fun to write the appendix. But there's an appendix in the paper that derives all the asymptotic variance stuff you want to make this usable. And there's Stata code. I don't promise that it's like the most efficiently written code. It's not in Meta and various other defects to it, but it's called the B1X2 module. And if you type SSC install B1X2, for those of you who use Stata, it'll grab it and you can use it. There is a help file as well. And I think there's some discussion on the Stata list. There's some incipient R code and maybe even Python code out there that does it as well, but I think it's not as complete as the Stata code for anybody who's interested. Okay, so our next point. Igor was talking, I can't remember what you said in your presentation, but you were talking about the Oaxaca-Blinder decomposition or a generalization of it through the Powers and Yoon work as well. This idea of decomposing things into differences, differences across groups in the part that's associated with, as Igor referred to it, exposure and vulnerability. That dates back to this Oaxaca-Blinder stuff, at least anyway. So this decomposition turns out to be more general than this one. You can show in the linear setting that this is Oaxaca-Blinder is a special case of mine. And I'll have more to say about that in just a moment. It also works with instrumental variables for those of you who are interested in doing ID stuff. If you have an exactly identified system, then you get the same numerical equivalence that I was talking about. If you have over-identified, if you have extra instruments, essentially, then it's true asymptotically, and I'm not going to say any more about that. There's a brief discussion in the paper. And finally, the extension of weight of least squares is really trivial. So I'm not going to say more about that, but it is actually important for one other thing I'm going to say more. I'll do this real quick. What about health disparities? I actually I'm going to switch. This is a paper that uses my decomposition. Igor sent this to me actually with obesity prevalence, area of the county level obesity as the outcome variable. Everything else is just the algebra is exactly the same. It's all linear, and you're not supposed to be able to read any of this. You obviously can. I barely can. But the point is that this is the kind of graph you could do to break down the decomposition into different components of the gap you're interested in. That just sort of shows you one kind of demonstration. Now, I want to say, Igor, the paper, the stuff you just presented, was that the paper that you sent me as well? It's the same or just related?
The same, but we have extension.
The same but different. Okay, so similar. That work studies black-white differences in Alzheimer's disease risk using various risk factors, as we just heard. And it uses a nonlinear version of the Oaxaca-Blinder decomposition into these exposure and vulnerability, or what economists would often call either characteristics and coefficients, or maybe quantities and prices, or something like that, depending on the economist and the topic. And that involves estimating a hazard model using piecewise Poisson approach. So it's a nonlinear model, unlike what I showed you above, and it leverages the Powers and Yoon paper that Igor mentioned in his presentation. The one thing I want to say about that is that decomposition is being done local to the mean of the x's, at least in the Powers paper. Whereas we often care about the mean of the nonlinear function evaluated at, sort of averaged over each observation's x. They sort of think they're often going to be close, but they don't always have to be. The extension I'm working on will actually handle that problem. So the extension I'm working on is actually going to extend all of this directly to the nonlinear kinds of settings. The main point I just want to make about that is it involves, instead of doing this gamma matrix I was talking about, the x1 prime x1 inverse x2 matrix, it's actually a weighted version of that. It turns out that we can handle all the nonlinearity, at least in most conventional models, with linear treatment of covariates. We can handle all of that with an appropriate weighting involving the likelihood function, or whatever the version of the likelihood function is if you're working in GLM or some other model like that. So I'm optimistic that all of what I'm talking about will have a straightforward extension into nonlinear locum, which is particularly relevant for this crowd from everything I've seen so far. So in conclusion, decompositions are, I think, really both useful and important for understanding which kinds of variables are driving our observed results. But it's really important to use conditional approaches. Adding one more covariate at a time and seeing what happens. I showed you on that first table, even in super simple linear world, just how destructive and problematic that can be. So I guess I'm just going to leave it there. So thank you very much.
Welcoming any question? One question.
Sit down too. Yeah.
Hate to just follow up on the question that I asked either earlier. So from your presentation, when I got it, even more critical or important is the IQ. Now, I'm not familiar with the test that was done in the veterans. And for us, we psychologists do extensive testing to establish the IQs. And even those, validation of those are difficult. Now, how sure are you of the whatever ACTQ test that you used and then the difference between the education and that those you combine, that's the impact of your IQ testing and overall on the prediction of SES or whatever?
So what I would say, it's a great question. What I would, I'm standing up here as a methodologist rather than a substantive guy who's telling you, it's really IQ that drives wage differences. That's not my.
But you're an economist.
Who knows what IQ picks, what AFQT, which is maybe IQ test or something. Who knows what exactly that's picking up? I have nothing invested in the idea that picks up something I need, or entirely possible that I would actually assume that some of what that's picking up is what people learned in school and so on. So I don't have. I'm afraid I don't have a great answer for you that's sort of going to take a stand on the AFQT test and what it tells us substantively. I'm just telling you that the variation in that variable has, sort of conditional on education accounts for a certain, and it turns out large, fraction of the explained wage gap. And so, this is a place where I would not even want to go near telling you, sort of that version of that.
But it makes
understood the
really do make sense that clearly it's just not simply purely education. It's beyond that.
Well, in fact, education is in the model, right? It's conditional on education.
Exactly.
So it's picking up something more than years of education. It might be picking up quality of education, or the nature of that education and aspects of it that vary beyond the number of years that people have.
Yeah,
for sure.
So, but even if it is education or IQ, there is an error in measure. And how much can this model really?
Yeah, so that's also a great question. If AFQT was something I had a really strong theory about, if that test score was something I really, really believed something about, and you came along and you said, yeah, but Gelbach is mismeasured, I would say, well, geez, we're going to have to start thinking about errors in variable models, and that's really complicated because we have multiple variables in this model, and we all know that that's a mess to say anything for sure about. What I would say is that whatever it is, AFQT as measured is picking up. That's what I'm telling you something like, right? I almost like I should have, instead of calling it AFQT, I should have called it A. Because I don't need to be making a strong statement about the IQ of people. But
thank you very much.
Yeah.